Okay, we're going to start with talking about some photo terminology. So we need to know the parts of the photo and what kind of ancillary data can be found on a photo. To the left is a schematic of a typical aerial photo. I should say that generally we're talking about 9 by 9 inch photos. So to give you an idea, if you look at a standard 35 millimeter photo, 9 by 9 is 228 millimeters by 228 millimeters, so much larger than a standard film camera. And we're going to talk about these as we go along. So first of all, we have vertical and oblique aerial photography. So at left, vertical photography means that you can draw a line between the center of the photo, the center of the lens, and um, the middle of the image. Okay, and that line is perfectly plumb. That is, it's directly down from the plane. Okay. A low oblique aerial photography. In that case, the plane or the camera is positioned in such a way that that center line is not not directly below the plane, but you can't see the horizon. A high oblique aerial photograph allows you to see the horizon. So the advantages of oblique photography is the more familiar viewing geometry. This is how we see mostly. You can photograph under clouds in some conditions, and the details of some construction is more easily viewed. And if you look at that top image, those are dwellings at Mesa Verde. And if you've ever been out there, you know taking vertical photos of those areas would not be very useful. The advantage of vertical photography is there's an approximately uniform scale throughout the photo, so you can make better measurements. The determination of directions can be performed in the same manner as a map. It's easier to interpret size than in oblique photographs. Tall objects will not mask other objects as much as they would on an oblique photo. So if you're looking sideways, you might see a building and that would mask anything behind it. And then vertical photos can be used to derive orthophotos, photos that can be used as maps that have constant scale, and then from that, topographic maps and digital elevation models. Now, those last pieces, the orthophoto piece and the mapping and potential for mapping using photos, was true that you can only do that with vertical photos when mathematical calculations were being done by hand or in a mechanical context. But now we have more complex ways of doing this. We have digital elevation models, and there's now a subset of aerial photography dealing strictly with looking off at low oblique angles and being able to capture more information about I've seen great images of forests looking at an oblique angle. You can see there in the bottom, urban areas. Certainly those are areas where you might want to see the sides of objects. So we have two concepts here that talk about where the photo is so to speak pointed. So the nadir of the photo is the point directly underneath the aircraft, perpendicular to the Earth's surface. And so it's essentially a line drawn between the middle of the photo, the center of the lens, and the center of the Earth. Okay, that's nadir. A tilted photo represents a slightly oblique view rather than a vertical view. So it's a little off nadir. And objects in the photo will have a small displacement, that is a small distance, from the positions they would occupy in a vertical photo. And in the center of the photo itself is the principal point. And in a nadir photo, the principal point and the nadir are the same point. In cases where the nadir is not the principal point, we have an isocenter that is, for calculation purposes, the center of the photo. In general, when there is less than a 3-degree offset between the principal point and nadir, they can be treated as vertical photos. In general, aerial photography is flown with stereo coverage. So what that means is we need to cover every point on the landscape twice. And so we need overlap between subsequent images. That is known as NLAP, and we generally have about 60% overlap to generate stereoscopic models. So that's 50% overlap because we have to capture each area twice, and an additional 10% as just a margin of error. Although 60% overlap is flown in general, if you want to improve the accuracy of height measurements, the relief, the vertical range, the appearance of it can be exaggerated by increasing the ratio of the stereo base separation of photos to the viewing distance. That is, you want to have the largest distance that you can have between two stereo photos that you're going to be using to create any kind of vertical map. And that means you need more photos because not every pair of photos is going to have that distance between them. And the effect is analogous to having a wide spacing between your eyes, which, as we'll see, increases a parallax angle that makes measurements more accurate. So we talked about NLAP. When we're collecting aerial photos, we generally have multiple flight lines, and those have between 20 and 30% side lap, again, as a margin of error, so that we have full coverage of the scene. You can see here that these photos are not perfectly lined up in a transect. Okay, that's because the orientation of the camera and the orientation of the plane is not exactly correct. Modern systems, we correct for this by using a stabilization mount. So the camera sits in this mount, and rather than having the effect of the plane changing its direction and coming up with photos that are not quite aligned, this allows you to change the direction of the camera in real time, so you get a more consistent orientation of the camera. You can see there on the right, you have a series of photos with and without the angular motion compensation. So that makes it much easier to work with a set of photos. Now we can deal with more parts of the photo. So this is peripheral data. Each photo has data, what we would call metadata about it. And these indicators are added to the film through devices that are in the frame of the camera. Okay, so the film is a little bigger, okay, than it needs to be, so that it overlaps these devices within the frame of the camera. So we have here we have a grayscale wedge, so that we can get calibrated values of how dark and light things are. 2 is a notepad, so you can actually draw some. It's a little piece of glass. You can draw things on that. 3 is an altimeter, so you know the elevation. We're going to skip 4 for the second. 5 is a clock, so you know the time. 6 is the lens cone ID. You need to have certain information about the lens cone in order to properly process images. So you have an ID for that, and you can look that up in tables to find out the specific qualities of the lens cone. 7 is the focal length, so the precise focal length. 8 is the frame number, so that's just the roll and photo for each image. 9 is the mission name, so that's again all part of the frame, so it goes on every photo. And then let's go back to 4. 4, these are fiducial marks, and again, it's part of the frame. This allows you to know how the photo was precisely aligned with the lens. And because if you connect the fiducial marks, okay, so there's a top one, there's a bottom one you don't see, and then there are the 2 side ones. If you draw lines between them, then the intersection is going to be the precise middle of the image. So fiducial just means a trusted entity or a reference. Again, fiducial marks are part of the camera frame. And then that principal point is located at the intersection of the fiducial marks. We have principal points and we have conjugate principal points, okay? So if we look at PP1, principal point, point 1, that's at the center of that first photo. If we look at that image, we're going to find that there's a road intersection there. You can't see it here, but just take my word for it. If we then go to the second photo, then that's where that intersection is on the next photo. Okay, so in one case, it's in the center of the photo. In the next photo, it's at the edge of the photo. And then we have a principal point 2 for that second photo. And the distance that the plane travels is between between shots is from the principal point of photo 2 and the conjugate principal point on that photo from the subsequent image. And that's known as the photo base. And the flight line connects each principal point through the conjugate principal point to the principal point 2. And as I said, the distance, when you actually put down the photos, between principal point 1 and conjugate principal point 1 is the photo base. Now let's talk about the geometry of stereo vision. When we focus on an object, the difference between the angles that our eyes have relative to each other is what tells us the distance to the object. So, and you can look over the left, we have at the bottom, that figures the position of the left eye and the right eye. When an object is close by, the parallax angle, the angle at the top of that triangle, is relatively large. The further away the object is, the smaller the parallax angle. And at a certain point, the parallax angle, becomes essentially constant, and we can no longer make meaningful distinctions between distances. When we're working with stereo photos, okay, you can look at the bottom. We have, we can look at the top. We have the plane at time A and the plane at time B, collecting photo A and B. And if we're looking at a tree in the ground, okay, the top of the tree has a point on the photo, right, where that tree shows up. Okay, it's going to show up at those two locations in each one of the photos. Similarly, the bottom of the photo is going to be have another position within each photo. And again, we have two parallax angles between the two positions that result in seeing the top of the tree and the bottom of the tree. And so in our viewing of a stereo photo, our eyes are essentially at the position of the camera when it took photo A and photo B. And so that allows us, when we look through a stereoscope, to identify the top and the bottom of the tree in 3 dimensions. So you get a 3-dimensional effect. On a single photo, the stereo effect causes displacement. Displacement is an apparent shift in the location of an object on the photo due to perspective view of the photo. Okay, what do I mean by perspective view of the photo? If we look at the figure at right, sort of naive perspective of looking at a photo or looking at a map is that you've got some terrain there at the bottom, and that the scale of that projection is reduced to be projected on a map or be projected on your eyeball as you look down. But in fact, that's not the correct geometry. What we have is a perspective geometry or a perspective projection where we're actually looking through a lens, and those lenses intercept the ground surface, okay, and then are projected into your eyeball. The difference at the lower left is that objects that are further away from the principal point will appear to lean over, okay? So if you look at those trees, the trees near the center, the principal point, is you're going to see, just the top part of each crown. As you get further away, you can see you're mostly seeing the side of the crown, and that's because you have perspective geometry. And you can see the effect if we look at the perspective versus the orthographic projection, just based on the geometry of where light is coming in to impinge upon the back of your eye or your retina, you're going to see the sides of objects, okay? And so at the top image, you can see the sides of buildings because of that geometry. Orthographic projection, you don't see the sides. You're always looking at the top of an image, and that can more or less be provided when you have a camera at very high altitude. So for instance, from space, those images, pardon me, in most cases give you, for practical purposes, an orthographic projection. We can calculate the amount of displacement with a very simple equation. Radial displacement, d, is equal to radial distance times the height or elevation of the object, and decreases with the flying height of the platform. So we have the principal point there in that red circle. we have two lines there, a line between that center, that principal point, and the bottom of a building, and another to the top of the building. The displacement of the building increases with the distance from the principal point and as the height of the building increases. Okay, so those two arrows, one points to the bottom of the building, one points to the top of the building. Presumably, those are directly above each other, or else the building falls over. So assume that they're the same, and as you go from the bottom of the building to the top, that displacement increases. Okay, and that's because the radial distance increases and the height of the object increases. As I was saying, as you get to higher altitudes, that is big H, the displacement decreases. And so that's why from space, you effectively have very little or no calculatable, no observable displacement. As with other equations, I will ask you how displacement changes with the various other components of this equation, but I won't have you do calculations. Here's another example using that equation. So if we look at that photo at the bottom left, we have the nadir of the photo, and then we have lines connecting it to two silos that have the same dimension, same height, and one is not only further away from us, but closer to nadir. And so you can see that you can see more of the side of silo B than silo A. Okay, so it's displacement is directly proportional to that radial distance from an object to nadir. It's also directly proportional to the height of the object, and then it is inversely proportional to flying height. Objects can be displaced either away or towards the principal point. Okay, so you have to imagine you've got a line going from the lens through an object. Let's look at the one that's boxed out in red, toward the average datum of the image. Okay, so the average elevation. If your object is above the average elevation, okay, you're going to see it at the point where the line intercepts the terrain or average elevation. And so it's going to be, for the case of A, circled in red, it's going to be away from, it's going to be displaced away from the principal point. Conversely, if we look at object B, boxed out in blue, that object is below the average elevation or the datum, and the line connecting that object and the lens is going to be displaced toward the principal point. So it's going to appear as if it is leaning into or towards the principal point. The displacement on photos changes the area that you calculate for, say, bar stands. So on the left, we have just a grid that's been placed onto the photo. You might use that grid to calculate the area of different cover types. On the right, the displacement for each one of the intersections of the grid has been calculated, and the grid has been modified so that there's actually an equal distance between each point and the next point. And what you see is not only do those points move, but depending on the topography, the area covered by each one of those grid, each element of the grid has changed. And so you couldn't use just a single photo when you have variable terrain in order to compare directly areas because of this displacement effect on individual points within the photo. So, review of displacement concepts. It causes features to appear at a different location on a photo than they would be on a map. Topographic displacement varies directly with height or depth of the feature or object, assuming everything else is the same. Topographic displacement varies directly with the distance from the nadir of the photo to the feature or object. It varies inversely or indirectly with the flying height above datum, which is why you cannot get stereo measurements from satellite images where the satellite is pointed as nadir. There is no displacement at nadir because the distance between nadir and nadir is 0. So that's the displacement must be 0. And then both tilt and in large extent photos, the curvature of the Earth can cause additional displacement, but generally we don't have to deal with that.